Welcome everybody to our poster about optical quality control of AR via near-eye displays. To fulfill the test requirements for near-eye displays, usually more than one light measurement device is required. The influence of gazing and rotation, for example, of the observer's eyeball is best examined using angular resolved measurements. Color and spatial uniformity of a display can be quickly measured by an imaging colorimeter with a specific objective lens. However, it is not trivial and sometimes even impossible to compare measurements performed by different measurement principles without a common reference base. Such a comparison is often required when results from one measurement, for example lab measurements, act as an input to another measurement, for example quality control in production lines. Here we demonstrate how an absolute calibration scheme based on reference spectrometers allow for accurate and swift comparison of complementary measurement principles. We use two light measurement devices, a goniometric spot meter with full angular and spectral resolution, and a fast, spectrally enhanced imaging colorimeter for highly resolved 2D images. Both devices use an absolutely calibrated spectroradiometer, fully traceable to a National Meteorology Institute, in this case the PTB. We use an Oculus Go and an Oculus Quest as a near-eye display test device. The DMS goniometer provides spot measurements covering a circular field of view from positive 40 to negative 40 degrees. The Lumitop camera system has a field of view of 120 degrees horizontally and 80 vertically. In order to compare the agreement of the two measurement principles, we first measure to the camera image of the DUT, and second, a goniometric light measurement device takes angle resolved spot measurements of the near-eye display. The luminance and chromaticity values from both measurements are compared and visualized in a 2D plot and with a corresponding histogram showing the differences of the two measurements. The results of the LCD-based Oculus Go device and the OLED-based Oculus Quest are displayed in the middle column of the poster. The agreement of the measurements are generally very good, with minor differences at the edges of the displays, where the spot meter practically averages over a gradient in luminance, while the high resolution of the 2D camera, on the other hand, provides a much finer sampling of the luminance. Even though the OLED spectrum is angle dependent and the LCD spectrum is not, our measurement devices need no DUT-specific calibration. They do not need that because they are by design calibrated to absolute values and therefore have no difficulties with changing display technologies, in this case LCD and OLED, or different measurement principles, like in our case camera versus goniometer. Reference measurements of a standard light source prove the close to perfect agreement between the two independent measurement devices. This assures that the influence of the measurement devices on the measurement results is negligible. From our experiments, we conclude that full optical characterization of near-eye displays requires complementary measurement principles which benefit from absolute calibration by swift comparability and high accuracy. Actually, absolute, accurate and traceable calibration of light measurement devices is a prerequisite for this comparability between the different measurement principles. No DUT-specific calibration, which is sometimes called golden sample calibration, is required, even across different display technology platforms when using absolute calibration of the measurement devices. Instrument Systems appreciates your interest in our work on highly accurate measurement devices for seamless and accurate quality control of near-eye displays from lab to fab. Thank you for your attention.